So welcome to the video lecture series on contact mechanics in the course M7033T. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. This is the third part of the first video lecture on contact mechanics fundamentals. And in this one you will learn about the complementarity problem. This video starts with describing the contact mechanics problem as a complementarity problem. Then we will go through two examples, one HERTZIAN case and one non-HERTZIAN case of the contact between two rough surfaces. So we know that if we have a certain pressure, then we can compute the deformation by this convolution expression. In this case we see that the dimensionless Hertzian pressure distribution, and if we insert it into the 2D problem for the 3D contact mechanics problem, then we obtain a deformation looking like the one depicted below. We know, however, that the pressure is actually the cause, or is actually caused by the contact between the two loaded bodies. And we need a problem to describe this.
You are probably wondering why we have visualized the negative of the deformation here, and this is because it is the deformation of the lower parabolically shaped half space that we will consider in the following example.
It turns out that that model or that problem is a school book example of a complementarity problem. And in terms of the contact mechanics, it reads like this. So when we have contact, we know that the gap between the surfaces are zero and the pressure is positive. And when we have no contact, the gap is positive and the pressure is zero. Now, in this complementarity problem, the gap and the pressure are the complementary dependent variables, which we need to solve the system of equations for. Let us consider a Hertzian example problem. So we have a rigid half space and we have a parabolically shaped half space which we bring to contact together under a certain applied load. The result will be a deformed half space and a corresponding pressure distribution.
The deformed body results from the contact between the original undeformed lower body and the rigid upper flat half space. Now the deformed lower body is therefore composed by the original undeformed lower body, the deformation of it, and the interference or rigid body movement or mutual approach. Dear child have many names, here denoted by delta. So if you add these three components together, you get the deformed lower body as a result. We note that the direction of the rigid body movement is also essential. So delta is a positive number, and according to the arrow, it shifts the lower surface upwards in order to bring it into contact with the rigid flat upper half space. The reason for visualizing the negative of the deformation before will hopefully become even more clear here when we generalize the previous problem one step. So this can be done by viewing the deformed lower body as the gap between the deformed surfaces, which we denote here by H. And the figure here depicts the negative of the deformed gap, which is, of course, equivalent to the lower deformed body. Similarly, the components can be generalized in the following way. So instead of the shape of the lower body, we consider the original undeformed gap between the bodies, denoted here by G, and with its negative in the figure. And we add the negative of the deformation and the rigid body movement or mutual approach. Let us add a few more details to this. The upper boundary of the lower body has already been defined as ZL. Now let's also define ZU as the lower boundary of the upper body. Then the original undeformed gap between the two bodies should be defined as the absolute value of the difference ZU minus ZL. And we know that G is non-negative, always greater or equal to 0.
At the contact points, the deformed gap is 0. And this means that the elastic deflection U at the contact points must be exactly inversely shaped compared with the undeformed gap between the two surfaces. Because it is only this way that we can add these two together with a certain shift, this interference delta, so that they cancel and become 0 at the contact spots.
We are finally at the stage where we can give a clear and concise description of the deformed gap between the two contacting bodies, as can be seen here. And now this holds true not only for the Hertzian solution or situation where the parabolically shaped bodies are brought into contact with each other. It also holds for any two bodies that can be considered as half spaces.
The previous example was for the Hertzian contact, but here we have a rough surface instead. But the same thing holds. So wherever there is contact, the pressure is positive and the gap is 0, and wherever there is no contact, the pressure is 0 and the gap is positive. Contact, no contact.